Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the problems on section modulus. So, what is the course outcome for this session or for this topic is related to the course outcome number 4. And the course outcome is apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stress, shear stress distributions and failures of beam sections. And the level of Bloom taxonomy for this session is apply level. And we are going to solve the problems. And here, what is the section modulus? Let us recapitulate here a little bit. Here, before going to start the problem, section modulus is the ratio of moment of inertia to the y maximum, is the distance from neutral axis to the fiber or topmost layer. This is known as section modulus. The unit for section modulus is unit for section modulus is millimeter cube. And and one more important formula for solving the problems is m equal to sigma maximum times z, where z is the section modulus and where m is bending moment or moment resistance. Bending moment or moment resistance. Sigma maximum is the bending stress. So here problem is that what is the problem here? The problem is a rectangular beam is having 300 millimeter deep, is simply supported over a span of 4 meters. Determine the uniformly distributed load, and uniformly distributed load per meter which the beam may carry. If the bending stress should not exceed 120 Newton per square millimeter, and take the second moment of area equal to 8 into 10 power 6 millimeter per 4. And the depth was given here 300 millimeter, L is 4 meters. The maximum bending moment can be observed at the midpoint. So here the UDL, we have to find out the uniformly distributed load for which we can carry the uniform distributed load the beam can carry. We have to find out how to find out this value here. The bending stress is maximum here at the midpoint C. For a simpler supported beam is carrying uniformly distributed load throughout the span of the beam. So here the point C, where the point C is there, we have to find out at this point what is the bending moment. That bending moment represents the maximum bending moment of this simply supported beam is subjected to UDL throughout the span. Now at that point C, what is the bending moment? Here it is 2W times 2 minus 2W into 1, that is 2 times small w Newton meter. Convert into millimeters, 1 meter equal to 1000 millimeters, that's 2W times 1000, that is 2000 W Newton millimeter. This is the M. And one more thing is that we know that M equal to sigma maximum times Z. And here the sigma maximum, then Z equal to, what is the formula here? Z equal to I by Y max. That I mass moment, that is second moment of area, I comes from BDQ by 12. Here it is given that is 8 into 10 power 6, and sigma maximum is 120 Newton per square millimeter. Now 120 Newton, yes. Now sigma Z equal to I by Y max. I is 8 into 10 power 6 by Y maximum, that is a D by 2, that is 300 by 2, that is 150 millimeters. This is the Z value. And what about sigma maximum? The maximum stress not to be failure is given here 120 Newton per square millimeter. Substitute over here 120 times Z 8 into 10 power 6 by Y max 150. So we know this bending moment, that is 2000 W, 2000 times what is the small value, that is uniform distribution load, is observed as 3.2 kilonewton per meter. So 120 into 8 into 10 power 6, after simplification, the value is observed in terms of Newton per millimeter converted into here. This is the value is observed. One more thing, one more problem is that the next problem is a very important problem here. This also here we have to find out the uniformly distributed load if the bending stress is not to exceed 120 Newton per square millimeter. Here it is a rectangular beam. A rectangular beam is of 200 millimeter deep and 300 millimeters wide. It is 200 millimeters deep and 300 millimeters wide width. And here it is the simply supported or a span of it is 8 meters, 200 millimeters deep, 300 millimeters wide, and it is over a span of 8 meters. Here L equal to 8 meters. Now what uniformly distributed load per meter the beam may carry if the bending stress is not to exceed, but the bending stress not to exceed 120 Newton per square millimeter. There is a sigma maximum. This 120 Newton per square millimeter is the maximum stress, and we have to find out what is the objective. We have to find out uniformly distributed load. Here it is simply supported. Now Z equal to, for this section, this figure indicates the section of the beam. The section of the beam is the rectangular, that is 200 millimeters deep and 300 millimeters wide. The rectangular section for this type, it is BD square by 6. Here B is the 300 millimeters, D equal to 200 millimeters. After substituting in the section modulus, that is BD square by 6, that is 2 into 10 power 6 cubic millimeters. Now after that, we know whenever the uniformly for a simply supported beam is subjected to uniformly distribution load WUDL. For that case, that is UDL is W Newton per meter, small w Newton per meter for a length L. Now for this case, what is the maximum bending moment? The maximum bending moment is occurred at the midpoint of the beam, that is becomes W, small letters W L square by 8. The W L equal to 8 meters, substitute here L equal to 8 meters, L square 8 square by 8, that is 8 W. Convert, it is in Newton meters, convert into Newton millimeter multiplied by meters. 1 meter equal to 1000 millimeters. So 1 meter equal to 1000 millimeters. Now what will happen? That means 8 W Newton meter, that is 8 W times 1000, 8000 Newton millimeter, small, this is the M. We know the formula, that the relation between section modulus and bending moment, and also the maximum bending stress, that is M equal to sigma times Z. What is the Z value? Z value already calculated, that is 2 into 10 power 6, and sigma maximum already given, that is 120 Newton per square millimeter. Here M value, that is 8000 W, small w times 120 into 2 into 10 power 6. So the small w is calculated here, it is 30 kilonewton per meter. Okay, after calculation is 3 Okay, 3 120s, that is 30 kilonewtons, 30 into 1000 Newton per meter, that is 30 kilonewton per meter. This is a small value, that is uniformly distributed load is calculated. The novelty of this problem is that the simply supported beam is carrying uniformly distributed load throughout the length of a beam. And one more thing here, for throughout the length of the beam, we have a formula of WL square by 8. That is directly. But suppose if it is partially for L by 2, it is UDL. Here it is UDL, that is W Newton per meter. And there is a point load is acting W1. Then how to find out the maximum bending moment, M value for this case study? What is the M? Then you have to solve the equations, unknown, the equations, and what is the bending moment value you have to calculate in terms of W or whatever the value it comes. But we don't have direct formula. We have to derive the formula. That formula that becomes the maximum bending moment value, where it will be maximum. Suppose if it is UDL, uniformly distributed load throughout the span of the beam, the bending moment is maximum at the center of the beam. Alright, the bending moment is maximum at the center of the beam. That's why we calculated the formula for this case is WL square, small letter W, that is UDL, uniformly distributed load, times L square by 8. W into 8 square by 8, that is 8W. So if it is different cases, if it is not uniformly, and then we have to derive the equation from the concepts of shear force and bending moment equations. Thus we have to calculate the maximum bending moment. Now one more thing is here, the next problem. Here the novelty of this problem, here it is comparison with point simply supported beam and also the cantilever beam, and we have to find out what to be found here, the uniformly distributed load on the cantilever beam. Now here it is a square beam of 20 millimeters by 20 millimeters in section. There is a section of the beam, and the span of the beam is 2 meters long, supported at the ends. Supported at the ends means it is simply supported. Next, the beam fails. Here the beam is going to fail when a point load of 400 newtons is applied at the center of the beam. 400 newtons is applied at the center of the beam. And what uniformly distributed load per meter length will break a cantilever of the same material having a section of 400 millimeters wide, 600 millimeters deep, and the span of 3 meters long? Now here, what uniformly distributed load per meter length will break a cantilever of the same material? Now here the simply supported beam, the square beam and the cantilever beam are having the same material. Material is same. What to be found? The objective here it is uniformly distributed load. What is the W? So the given data is that depth equal to 20 millimeters and width equal to 20 millimeters. It's a square beam, and length equal to 2 meters and W equal to 400 newtons. So the maximum stress for this case study, what is the case here? The simply supported beam is subjected to a point load at the midpoint. So for this case, what the bending moment comes from that sigma maximum you have to calculate. Now first you have to consider the simply supported beam, and from that maximum stress to be calculated first, and as the material is same for here simply supported cantilever beam, so hence the maximum stress also same. It will be same for both cantilever and also simply supported beam, and means sigma maximum is same. for sigma maximum for simply supported is same for cantilever beam. Alright. Why it is same? Because the material is same. That's why maximum stress. And one more parameter also same. Modulus of elasticity also same. E for simply supported beam equal to modulus of elasticity for cantilever beam. Now let us calculate the section of the simply supported beam is a square cross section 2020. From that, what is the section modulus? The section modulus is BD square by 6 or D cube by 6. So 20B, 20D, that is 20 square by 6. After substitution, the value of section modulus is 4000 by 3 cubic millimeter. And for a simply supported beam is carrying a point load, and the maximum bending moment is becomes at midpoint, that is W times L by 4. What is the W here? 400. There is a point load, the load which is acting 400 newtons. 400 newtons in times length, that is the span, that is 2 by 4. So 400 times 2 by 4, that is 200 Newton meter. Now here, this Newton meter to be converted into Newton millimeters, because we are following the dimensional homogeneity, it is in millimeters. So 200 into, that is meter, 1 meter equal to 1000 millimeters. Substitute over here, 2 times into 10 power 5 Newton millimeter. Now what is the sigma maximum? That is the maximum stress. The relation for the formula which is having a relation between bending moment, bending stress and section modulus, that is sigma m equal to sigma maximum times z. So what is the m here? 2 into 10 power 5 sigma maximum times z value, substitute here. From that, maximum stress can be calculated. That is 150 Newton per square millimeter. Sigma maximum equal to 150 Newton per square millimeter. Now this sigma maximum value is same for both cantilever and also simply supported beam. Now we have to consider the cantilever beam. In this cantilever beam, this figure indicates cantilever beam having is subjected to UDL throughout the span. The span of the beam is 3 meters. Now what is the section of the beam? The section of the beam is rectangular, that is 40 millimeters width and 60 millimeters depth. Now here, what is section modulus formula? That is BD square by 6. So B equal to 40, D equal to 60. 40 into 60 square by 6, that is 24,000 cubic millimeter. Now what need? We know sigma maximum, we know Z. That we know the relation between moment resistance, sigma maximum and section modulus. The section modulus value is here 24,000. Sigma maximum here it is, that is 150 Newton per square millimeter. We want, objective is that uniformly distributed load. For a cantilever beam is subjected to uniformly distributed load. What is the bending resistance? So the maximum bending moment for such cases is WL square by 2. It is small letter, the UDL. W, what is the L? Span of the beam 3 square by 2. That is 4.5 W Newton meter. It should be converted to Newton millimeters for dimensional homogeneity, because all units are in terms of millimeters. So 4.5 W into 1000, that is 4500 small w Newton millimeter. This W in terms of small w, now we know the relation between M sigma maximum and section modulus. The formula here it is M equal to sigma maximum times section modulus. And substitute what is the M value and sigma maximum value and Z values. And in that M value there is small w. That small w is known as uniformly distributed load. Let us substitute here. 4500 W, that is 4.5 times 1000 W. Sigma maximum, that is 115 Newton per square millimeter, and section modulus Z is 24,000 cubic millimeter. Then W equal to 115 to 24,000 by 4.5 times 1000. This is 800 Newton meters. They calculate here. It should come the value Newton per millimeter. So after simplification, it comes in this value. 3 get cancelled. So simplification, you will get it the value in terms of millimeters, that convert into meters. Then this is the value, that is 800. Alright. So this is the UDL consideration. It is approximately 800 Newton millimeter. Okay. Newton meters. Now that is the case for that we calculated in this problem. So unique problem here it is. The concept behind this is the same material mentioned in this problem. Same material means there are two considerations. One is maximum stress is equal, or another condition is that from that we can interpret that modulus of elasticity also same. But the beams are different. One is simply supported beam, another one is cantilever beam. For a simply supported beam, from that first we calculated the maximum stress, so at which the beam get fails. The same material here, the condition is that same material, that's why we consider sigma maximum stress. The stress remains the same for both the beams. That sigma maximum, with the help of that section modulus Z. So from the first case, from simply supported beam, by using section modulus and moment resistance, we calculated the sigma maximum. Okay, and by using the sigma maximum, for the case we applied that value on the cantilever beam, and this cantilever beam here it is subjected to UDL, uniformly distributed load, throughout the span of the beam. So throughout the span of the beam it is uniformly distributed load. So where we used again, what is the moment resistance? The moment resistance for that, when the beam is subjected to UDL, throughout the span of the beam, this is WL square by 2. That is W into L square. From this we obtain the unknown value, that is final value, that is uniformly distributed load of cantilever beam. And here one thing is very important for the maximum stress. The maximum stress here it is 150 Newton per square millimeter. But the section modulus for cantilever beam is having a different cross section. That's why the section modulus of simply supported beam section and the section modulus of cantilever beams section is different, but it is made of same material. That's why the sigma maximum is considered same for both the beams. The next problem here very important problem for calculating the span of the beam. Here it is. So far we covered what is the maximum stress or failure stress, what is the moment resistance, and another one is that for calculating the uniformly distributed load. In this problem we are going to calculate or determine the span of the beam. Now how to start the beam here? What is the problem here? The sum here it is, a beam is simply supported. Is it clear? The beam is simply supported, and what type of load it is being carried? It is being carried a UDL, uniformly distribution load of 40 kilonewtons per meter run over the whole span. The section of the beam is, what type of section here? It is rectangular, having a depth as 500 millimeters. If the maximum stress in the material of the beam is 120 Newton per square millimeter, and moment of inertia of the section is, I value was given here, that is 7 into 10 power 8 millimeter per 4. Find the span of the beam. What is the span of the beam? That is L. So what are the inputs given? UDL, that is 40 kilonewton per meter, that is 40,000 Newton per meter. D, depth is 500 millimeters, maximum stress 120 Newton per square millimeter, and moment of inertia of the section I, that is 7 into 10 power 8 millimeter per 4. L is the simply supported span of the simply supported beam L to be found out. And let us begin how to start. So this L comes again. We have to use two formula here. One formula M equal to sigma maximum times section modulus Z. So in this M, moment resistance when the beam is subjected to UDL throughout the span of the beam. So okay, at the midpoint we have to find out, that is W Newton per meter. That was given, here it is, that is 40 kilonewton per meter. But we have to find out this length L. Okay, now let us begin. What is Z? Z value could I by Y maximum. Here it is whatever section here. I value is given directly 7 to 10 power 8 millimeter per 4, and Y maximum, that is D by 2, that is 500 by 2, that is equal to 250 millimeters. Substitute Y maximum and I values in Z equal to I values 7 to 10 power 8, Y maximum 250, that is 28 into 10 power 5 cubic millimeters. Now when the maximum bending moment observed for a simply supported beam is having UDL over the whole span, for that case that is WL square by 8, where small w is uniformly distributed load. So small w, that is 40,000 Newton per meter. L should be, okay, and 40,000 L square by 8. We need, it is in Newton meter value. Why? Because 40,000 it is in Newton per meter. So 5,000 L square Newton meter it should be converted into Newton millimeter for maintaining the dimensional homogeneity. So 5,000 L square times 1000 Newton millimeters. Now M equal to sigma maximum in times Z. We know M value in terms of L square. Sigma maximum 120 Newton per square millimeter. Z value 28 into 10 power 5. From this the unknown value can be found. That unknown value is the span of the beam. That is L equal to 8.197 meters. That is nothing but 8.2 meters. L equal to 8.2 meters. That is the span of the beam. So here, what to be here in this session, we solved various problems, especially various model. There are 3 models are covered. One model is that finding out the bending stress. Second model is calculating the uniformly distributed load. And third model is calculating the span of the beam. And one important model also covered here by comparing here the 2 beams, one is simply supported beam, another one is cantilever beam, and it is having same materials but different sections. And one cantilever beam is subject to UDL and simply supported with point load. Because it is having the same material, we considered in this case the maximum stress is same. Thus we found out the value of uniformly distributed load over the cantilever beam. So these are the important, and the references we followed in this textbooks here, Subramaniam, Ramamuratam, which are strength of materials, and reference books by Loboda, Mechanics of Solids and Materials, the Cambridge University Press, and Vajirani and Ratwani, the Analysis of Structures. And one more, these are the websites followed, and with the help of these websites, and we collected the materials and concepts in this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.